Euler's formula is an identity that is found everywhere in complex analysis, when working with complex-valued functions, and is also used when evaluating certain expressions involving complex numbers. The famous identity is e to the power of I theta is equal to cosine of theta plus I sine of theta, where theta is a constant and I is the imaginary number I. What we're going to do in this video is prove this identity using Taylor series. So here are the Taylor series we will use in the proof. These are all Taylor series centered around x equals 0, so these are also Maclaurin series. So the Taylor series of e to the power of x, centered around x equals 0, is the sum from n equals 0 to infinity of x to the power of n divided by n factorial, and that just turns out to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. There's a generalization of this Taylor series, which is the Taylor series of e to the power of ax, where a is a constant, and that's just the sum from n equals 0 to infinity of ax all raised to the power of n over n factorial, and that just turns out to be 1 plus ax all squared over 2 factorial plus ax all cubed over 3 factorial, and so on. There's also the fairly well-known Taylor series of cosine x and sine x. So the Taylor series of cosine x, centered around x equals 0, is just equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. And the Taylor series for sine of x is just x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. And these are all the Taylor series that we will be needing for the proof. With all these tools we need for this proof, let's get right into it. Let's start with the left-hand side of the identity, e to the power of I theta. This expression is equal to its Taylor series expansion, which is the sum from n equals 0 to infinity of I theta all raised to the power of n divided by n factorial. What we're going to do here is apply the Taylor series expansion for e to the power of a theta, which we just went over, where in this case, a is equal to the imaginary number I. So let's just write out the first few terms of the Taylor series expansion. So the sum is just equal to I theta all to the power of 0 over 0 factorial plus I theta all to the power of 1 over 1 factorial plus I theta to the power of all raised to the power of 2 over 2 factorial plus I theta all cubed over 3 factorial, and we'll write out more terms here, and you'll see why I wrote out so many terms in a second. So I theta raised to the power of 5 over 5 factorial, and I'll continue this until we get to the term I theta all raised to the power of 7 over 7 factorial. And there's going to be more terms after this, since there's an infinite number of terms in the Taylor series. The next thing we should do is rewrite all the terms without parentheses. So I theta all raised to the power of 0 is just I to the 0 theta to the 0 over 0 factorial. And the next term is just I to the 1 theta to the 1 over 1 factorial. And plus the next term would be I squared theta squared divided by 2 factorial, and so on. And this pattern will continue consistently for each term, so we just need to finish writing all of these terms in this format. So I to the 5th theta to the 5th over 5 factorial plus I to the 6th theta to the 6th over 6 factorial plus I to the 7th theta to the 7th over 7 factorial, and this series will continue with an infinite number of terms. We can use our knowledge of the powers of I to simplify these individual terms. So I to the power of 0 is just equal to 1 in the first term. So this is just equal to theta to the power of 0 over 0 factorial. I to the power of 1 is just equal to I. So this entire term is just I theta to the power of 1 over 1 factorial. I squared, as we know, is equal to -1, so instead of I squared theta squared over 2 factorial, this thing is just equal to minus theta squared over 2 factorial. I cubed is equal to -I, so the fourth term, I cubed theta cubed over 3 factorial, just becomes minus I theta cubed over 3 factorial. The powers of I are cyclical and repeat itself for every multiple of 4 in the exponent. So this means I to the 4 is equal to I to the 0, I to the 5 is equal to I to the 1, I to the 6 is equal to I to the 2, and I to the 7 is equal to I cubed, and so on. So we'll see a clear pattern if we continue simplifying these individual terms. So I to the power of 4 is just equal to I to the 0, which equals 1. So this term can be simplified as theta to the power of 4 over 4 factorial. I to the power of 5 is equal to I to the power of 1, which is just equal to I. So this term just becomes plus I theta to the power of 5 over 5 factorial. I to the 6 is just I squared, which equals -1, so this is just minus theta to the 6 over 6 factorial. And I to the power of 7 is equal to I cubed, which is equal to -I. So the I to the power of 7, theta to the power of 7 over 7 factorial term just becomes minus I theta to the power of 7 divided by 7 factorial. And the terms will continue because this is a Taylor series with an infinite number of terms. The next thing to do is to separate this expression into its real and imaginary parts. So we can see that we can rewrite this expression as theta to the 0 over 0 factorial minus theta squared over 2 factorial plus theta to the 4 over 4 factorial minus theta to the 6 over 6 factorial, and this series continues. And then the imaginary part, which is plus theta to the 1 over 1 factorial minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial minus theta to the 7 over 7 factorial, and so on. And all of this is multiplied by the imaginary number I. We can simplify the first term in both series by rewriting theta to the power of 0 over 0 factorial as simply 1, and then the rest stays the same. Theta squared over 2 factorial plus theta to the 4 over 4 factorial minus theta to the 6 over 6 factorial, and so on. And then theta to the power of 1 over 1 factorial, well, that's just equal to theta, and then minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial. This all stays the same, and then so on, and then this is multiplied by I. So we can start seeing a pattern here for both the real and imaginary parts. The real part always consists of the even powers of theta, which alternate between positive and negative, and for the imaginary parts, they consist of all the odd powers of theta, which also alternate between positive and negative. Since the powers of I repeat itself for every multiple of 4 in the exponent, this pattern is guaranteed to continue. Well, alright, let's look at both series. 1 minus theta squared over 2 factorial plus theta to the 4 over 4 factorial minus theta to the 6 over 6 factorial, and so on. Well, this is actually just the Taylor series for cosine of theta, which we covered earlier if you look back in the video. So we can just rewrite this as cosine of theta. And then the second series here, theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial. Well, this was just the Taylor series for sine of theta, which we also covered earlier. And then all of this is multiplied by I. So this is just I sine theta. It's just I times this entire series here, which is equal to sine of theta. So it's plus I sine of theta. And look, that's exactly what we were trying to prove. We started with e to the power of I theta, and we ended up with cosine of theta plus I sine of theta as our expression. And this shows that e to the power of I theta is equal to cosine of theta plus I sine of theta, because we started off with e to the power of I theta, and after applying some algebra and Taylor series, where each step along the way, the expression was equal to the previous expression, we ended up with cosine of theta plus I sine of theta. There are definitely other ways of proving Euler's formula, but this was the original method used to derive the identity in the first place, and probably also the most common.